Welcome everyone to this new video about an interesting technique relating complex number theory with trigonometry. In specific, we are going to apply the Moivre's theorem for integer powers to derive trigonometric identities. As a reminder of the theorem, when a complex number r at the phase of theta is raised to an integer power n, then the result is r to the power n at the phase of n theta. This is the polar form of the theorem. In rectangular form, it can be written as r times cosine theta plus j sine theta all to the power n is equal to r to the power n times cosine n theta plus j sine n theta. And since this equation is true regardless of the value of r, we can set r to 1 and obtain a simpler version of the equation. Cosine theta plus j sine theta all to the power n is equal to cosine n theta plus j sine n theta. This equation will be the starting point for deriving equations that relate cosine n theta and sine n theta to cosine theta and sine theta. All what we need to do is expanding the left-hand side, then comparing its real part with that of the right-hand side, which is cosine n theta, and also comparing its imaginary part with that of the right-hand side, which is sine n theta. Let's demonstrate this through an example. We want to determine the trigonometric identity that expresses the tangent of 2 theta in terms of the tangent of theta. But since our starting equation above deals only with sines and cosines, we have to adjust our problem accordingly. Tan 2 theta is actually sine 2 theta divided by cosine 2 theta. And tan theta is sine theta divided by cosine theta. So, writing tan 2 theta in terms of tan theta is equivalent to writing sine 2 theta and cosine 2 theta in terms of sine theta and cosine theta. To do that, we start with the equation derived above, but we customize it specifically for our need in this problem. This is done by setting n equals 2. This way, we will get cosine 2 theta and sine 2 theta as the right-hand side, just as we are aiming for. We now expand the left-hand side to first term squared, giving cosine squared of theta, second term squared, giving j sine theta all squared, or minus sine squared of theta, and 2 times the first term times the second term, giving j2 sine theta cosine theta. We now compare real parts on both sides to get cosine squared of theta minus sine squared of theta equals cosine 2 theta. We also compare imaginary parts on both sides to get 2 sine theta cosine theta equals sine 2 theta. These two equations are exactly what we originally wanted, cosine 2 theta and sine 2 theta in terms of cosine theta and sine theta. What remains now is to translate these to tan of 2 theta in terms of tan theta. So we write tan 2 theta as sine 2 theta divided by cosine 2 theta. Then substitute sine 2 theta as 2 sine theta cosine theta, and substitute cosine 2 theta as cosine squared theta minus sine squared theta. Divide the numerator by cosine squared theta and do the same at the denominator. This will reduce all terms to combination of constants and the ratio sine of theta divided by cosine theta, which is tan theta. So the final expression of the identity is tan 2 theta equals 2 tan theta divided by 1 minus tan squared of theta. The process might appear to be a bit lengthy or complicated, but with more practice, you will start feeling more confident in such kind of problems. In the next video, we will derive the identity expressing secant of 3 theta in terms of secant of theta. Until then, stay safe.